We're ready now to move on to chapter 8, and the topic here is something called confidence intervals. What we're going to do today is talk about the basics, the overall structure, some of the terminology of confidence intervals, why they're important, what they are, and how we're going to work with them. Now, everything we've done up until now in the entire semester has essentially been describing a circumstance that already exists, that we already know about. Up until now, essentially everything we've done with a population, we have been given the population mean. We have been given the population standard deviation. In many circumstances that you'll encounter, that is not always possible. That's not always available. Very often, when you want to do research in a new area, some sort of a field where you're doing research at asking a question that no one's ever considered before. You don't know what the population mean is. You're trying to find out how the population is behaving. You don't know the population mean. You don't know the population standard deviation. So a lot of information is not known, and what we're going to begin to talk about is using the principles and the ideas that we have so far to begin to learn about a circumstance where we don't know what's happening yet. Now, one way to do that is to use what's called a confidence interval. Now, let's suppose that we're doing research in animal husbandry, and so we have a wide group of cattle, let's say in Montana, that have been exposed to a toxin in the biosphere. And we want to know if that exposure is causing, let's say, low birth weights of calves among the cattle that have been exposed to this toxin. And so the question is, now, no one has ever done this work before. No one knows how the population behaves. We don't know if the population mean is greater or less than, or how it compares to the population of calves that are not exposed to the toxin. Now, the population of calves that have not been exposed, that population is well studied, well known, well understood. But now we have a separate population, those population of calves that have not been exposed to this, whose mothers have not been exposed to the toxin. And so we want to be able to measure those and gain some sort of an information about what we think that population will, how that will be. Now, let's suppose that we take a random sample. Suppose we take a sample of, let's say, 70 of these calves. This is a sufficiently large sample to meet the requirements of the central limit theorem. And so if we take our sample of n equals 70 calves, let's suppose, and I'm just going to make up numbers out of the blue sky, let's suppose that our sample mean is computed to be, and again, I have no idea what a reasonable number is, so I'm just going to slap a number down in here and not worry about the accuracy or the units. Let's suppose that value is 110. And let's suppose the standard deviation we compute from our sample is, again, I'm going to pick a number out of the blue sky. Let's say 9.1. Now, the question is, based upon the information we have gleaned from our sample, what do we think we understand, or what kind of information can we glean about the population values based upon the sample values? Well, there ought to be a couple things that are clear. Number one, we do not expect that the population mean will be precisely equal to this sample mean. Remember, we are randomly choosing 70 out of a potentially vast population numbering in the hundreds of thousands. And so we've only taken 70 out of that population. So we don't expect that this sample mean value is precisely equal to the population mean value. Another thing we know, theoretically, a person could compute the population mean. A person could, in principle, measure all calves born to all cattle have been exposed to this toxin, and in principle at least, a person could do that and find that value, find that number mu. That would be very expensive, very time consuming, very problematic. And so what we want to do is use the information we have garnered from the sample and project that to what we understand about the population using the tools we've developed so far, and see if we can get some information about how the population is behaving. Now, one thing that is working for us, and this is the key to all of this work, is the sample size is sufficiently large, and so we know the population of sample means is approximately normally distributed. We know that we get to use the normal curve. And that gives us a lot of information because, among other things, we have all of our data value from the normal curve. We have the principles and the computations and the formulas from the normal curve. What do we know about this? We know that this is the standard scale centered at 0. This is the data scale. These are the X bars. What we have done is we have reached into this number line essentially by taking our 70 cattle and measuring their weights and finding the average. What we have essentially done is reached in here and essentially blindfolded ourselves, reached into this bag and pulled out one of these sample means. It's possible that the sample mean we found, X bar 110, might have come down from this end of the scale. We might have gotten 70 animals that are particularly smaller than most. Or we might have gotten, our value X bar might have come from up here. We might have actually gotten several animals that are larger than most. But what is most likely to have occurred is that the sample mean we compute will probably have come from somewhere here in the middle. Now, what do we know about the sample means? We know that they are centered at the population mean mu. We don't know what that number is. We don't know. That's what we want to find out. And that's what our investigation is going to try to give us some information about. We want to use the information we have to find out where we think this population mean will fall. All right? So that's the procedure, and that's what we're going to pick up with on our next video.